4.
You're listening to Coding Blocks, episode 84. Subscribe to us and leave us a review on iTunes, Stitcher, and more using your favorite podcast app.
And check us out at codingblocks.net where you can find show notes, examples, discussion, and a lot more.
Send your feedback, question, and rants to comments at codingblocks.net. Follow us on Twitter at codingblocks or head to www.codingblocks.net and find all our social links there at the top of the page. And with that, I'm Alan Underwood.
I'm Joe Zach.
And I'm Michael Outlaw. So this episode, we're going to be talking about some common algorithms that you should probably be familiar with because they're going to come up in an interview and because many real-world algorithms that you'll need to come up with might be similar to these, or at least these will give you a foundation as to how those might be better. These are the types of things that are either for a review for CS or what you might have missed.
So I love writing the sentences that you end up reading because I feel like I'm throwing like the jungle gym at you. Now, I can give you like the obstacle course. I'm so amazed that you made it through that at all.
There's random words just pasted on the screen, right?
Yeah, man, I'm sorry. Like that sentence was not meant to be read. Not by humans.
No, I could tell when he was reading. Like that doesn't make it. Gotta make sense.
I was twitching a little bit, but now I know why. I thought I just like forgotten some medication or something.
No, man. I just kind of flopped that out there. All right. Well, thanks for doing that. So a bit of podcast news. Up first, we're going to talk about those reviews. You know we love them. Big thanks to everybody who left us a review, past, future, present. And first up, iTunes. Thank you, A. Keith 47. Thinking with my hair brain. T. Tordo Dove. Mero IT. Your worst enemy. Fiery Ginger. M. Car 86. Josh Rain Van. Michael Not an Outlaw. And then we got Michael Joe Allen, Serial Killer.
Now, wait a minute. Are you sure it's not M-Char?
That dude, I was right there. I was like, no.
Oh.
But it's actually car. It's got to be because you say Varcar. You don't say Varchar.
That's right. That's right.
Yes.
What?
All right. Yeah. I've got Stitcher. How'd this happen? All right. So I've got Liam M., Daniel 65, CB Fan 762904549, and Radulin.
Yep. So thank you always to everyone who has taken the time to leave us a review and everyone that is leaving us a review. We always greatly appreciate that. And so real quick, I do want to mention kind of a callback to going back to episode 1, maybe. I know especially Joe, we've talked about many times, had some feature requests for interfaces that he just wanted to have. Number one that always stood out in my mind was he wanted to have a default constructor for the interface, if I remember right. So it's not quite going there, but I thought, Joe, you might be happy that there is a proposal for C# 8 for default interface methods. And we've talked about this, I forget how many episodes go back, where Java actually already has something like this. And the C# team, they're actually kind of modeling, they're looking at the Java implementation for kind of like best practices or what worked, what didn't work. Try to like, we've said this before, like how we're always building on the shoulders of the giants before us, right? And so they're kind of looking at the Java community to see like how that worked and whatever. And so there's an article there that I got for you I thought you might enjoy where it shows some of this in action. And this will be, backwards compatible. You'll be able to apply these default interface methods to your interfaces that already exist in the wild.
That's crazy.
Yeah, you know what? The old me used to would have loved that, but I'm JS now.
Oh,
Yeah, I'm full on arrow syntax, everything. Denaturing stuff,
So wait, you're not into the TypeScript thing then? You're going all ECMA 2015 or whatever?
2015, ES6, yo. Can you tell by my attitude, my backwards hat?
Oh, that's right. There we go.
Oh, that failed.
That's right.
That was awkward. All right. So I also want to mention really quickly that we've been releasing a ton of videos. In particular, I want to call out the Community Talk number 2, where we got 5 of our favorite people on a call here. And got a great presentation on cross-platform development with Rad Studio from Zach and Ted. And we got a video up there on YouTube. I want to specifically focus in on the fact that we have a survey in there, a SurveyMonkey link that you can fill out. That's in that description and actually on the blog too. And you can win one of $400 gift card / shirt packages. So it's 4 prizes, $100 gift card and a shirt if you go fill out that form. So go check it out. You'll get a free trial too. That's good up for 9 months. So go do that before July 6th. So do it now while you're thinking about it and make some money and check out cross-platform development.
With Rad Studio. And I do want to say, we were all surprised by how cool some of the features were. So don't dismiss it out of hand when you just hear Rad Studio. Like, there was some really cool stuff shown in that video.
Exactly. Yeah, there was definitely some wow moments, some jaws hit the floor kind of moments. Which reminds me too, we always talk about subscribing to the podcast, but if you haven't subscribed to our YouTube channel, you should definitely take this as an opportunity to do so, or use it as an excuse to do so. You can head to www.codingblocks.net/YouTube for the easy way to get to our YouTube channel, and you can subscribe to us there, and that way you won't miss any of these amazing videos.
Hey, you want to guess how many videos we have?
Does this include episodes?
Yep.
I'll say 68.
Oh man.
Well, we have 80. We have every episode up there.
Oh, every episode.
Yeah.
I didn't realize we had every
All right,
episode.
we'll go with 95.
So we have 115.
Wow.
Which means we have 32 videos that are not episodes. And one of those videos has like 60,000 views?
Really? Is that the laptop one?
Yep.
Very nice.
Sure enough.
Awesome.
Yeah, and you want to guess how many views we have total if you were to go through and add up all of those?
14.
14.
Oh, wait. I might be missing that other 60,014.
Let's go with 250,000 views.
Oh, man. We have 95,000 views. Unfortunately, they all dropped off after about minute 2 when we started talking about like meta type stuff, like how our YouTube channel is doing.
Right. Yeah. All right. So moving on.
Move along.
Did you mention your QIT diary video as well?
Well, it's not really my diary anymore because we had 5 people on the last one, all talking about different changes and different ideas we have with the app. So if you haven't checked out QIT.cloud, highly recommend it. It lets you find podcasts by topic. So you can search like, say, GraphQL and find all the podcast episodes on GraphQL and solely focused on programming topics. So if you like programming podcasts, and I think you do, then you should check it out. You should check out the videos if you're interested in building software, because I also think maybe that's an interest that you have. And you're going to see some of your favorite people from Slack hopping up on that video talking about the different things that they're trying and working on in terms of the app, because we're up to 9 contributors now.
Yeah, it's really cool. And the video does go over sort of like what you do in a business. Like, these are the features we're thinking about adding, maybe we put it here, maybe we put it there. So it is kind of interesting to see the collaborative approach to it, not just on GitHub, but also in real life, right? People discussing the things and the reasons why they're choosing to do things certain ways. So it's pretty interesting.
One of my favorite topics is what we said we'd work on last week and what we actually worked on. It's kind of funny to see that disconnect. But hey, this is a fun project, so you can work on whatever the heck you want. It's awesome.
Super cool. And so I wanted to bring up something that's come up from several different people now. And I think that it's worth revisiting. Our last episode was on search, right? Like we kind of deep dived into the reasons why and that kind of stuff. And I think along the way, I think I even said that, maybe it sounds like we were cheerleaders for it. And I want to back up, because one of the things that has been asked a couple times right now is, well, why wouldn't you just use a data warehouse instead of a search engine? Or why wouldn't, we talked about aggregating and get aggregates back when you do your searches. Why wouldn't you just use a cube, or some sort of OLAP type processing? And while this is not going to be a comprehensive answer, I'm going to give you some of the reasons, and love for Joe and Mike to jump in as well. But here's the thing. search engines aren't perfect for everything. And I'll give you a perfect example right now as to why. When you are sticking something into like a Lucene-based type search index, you have to denormalize all that stuff into one document, right? Anything that you want to be able to search on that thing. Now, that's not 1000% true because there are ways around it. But generally speaking, if you want your search to be fast and you want it to be scalable, if that's the thing, like if you're using Elastic, you have to denormalize all the data that you want to be searchable and sortable and able to be aggregated into one document. So there, if you're comparing that to something like a data warehouse, obviously in a data warehouse, you can join tables, right? You have these things like star schemas. So if all of a sudden you decide that you need something from table Z over there, you can join to it, right? Through however many joins you need to do to get to it. So that's one reason why search engine isn't perfect for everything. It's not a relational database. It's not even a relational lookup, right? It is literally put everything you want in this thing that you want. Now, let's get into why I don't think that data warehousing necessarily solves that problem. A perfect example for me is one-to-many joins, all right? When you have something in a data warehouse and you want to get a perfect example is when you go to Amazon and we talked about cameras last time, right? You go into the camera category and now you're going to have DSLRs, mirrorless, point and shoot, whatever, right? And then there's going to be different things down the side that have sensor sizes and there's going to be counts associated with all those. Think about what you got to do in a SQL query to get those counts back. You're going to be grouping by all these different types and that is expensive, right? Even if you put it in one table and you don't have this join, which you wouldn't really do in a data warehouse because typically you'll have your fact tables that generally have as much of the data as possible, but those things are going to get really big. And even doing the group bys in those is going to be slow trying to get that kind of stuff. And then when you take it a step further and you want to do something like paging and sorting on these columns, anybody who's messed with SQL enough knows that when you do those, and I'll talk specifically to SQL Server right now, you have to index on the things that you want to search by. So now you're going to have a ton of indexes on these things, and indexes are typically done either ascending or descending, and they're going to perform properly based on what you do. So now these searches and these aggregations and all those things kind of fall flat because even a data warehouse is not necessarily meant for search. And it's not meant for paging and it's not meant for sorting. It's meant to be this place where you can go get all the data in a certain denormalized form. So going back to something like fuzzy searching on a search engine, you can't necessarily do that with a data warehouse, right? And you're sorting on columns and getting your counts and your paging and all that kind of stuff is not as easy. It just doesn't work that way. And then the OLAP thing, bringing that one in, that's a different tool for a different use case. So typically when you're looking at OLAP, you're wanting to be able to slice and dice data, as many possible different ways as you can. And this also goes back to the difference between what that technology provides for you versus something like a search engine or even SQL. That is the ability to look at data. And when we say slicing, if you have a cube and you want to draw a line down through the middle of that thing, that's one way to slice it. If you want to do it from a different angle, you can do it that way. But that's the relationships of the data. If you think about a cube, typically what it is if you equate that to like an Excel workbook. You have an Excel workbook. In that Excel workbook, you have many sheets in that workbook, and then there's tons of cells on those. That cube allows you to drill down into those points in that thing and relate these things all kinds of different ways. Search isn't meant for that. So when you do something like search, when we're talking about aggregations, we're talking about simple counts, right? Like that left-hand nav on the camera search on Amazon. All those counts of those particular keywords that showed up. So the CMOS sensor size, that kind of thing, right? That's what goes there. When you're talking about cube, you're going way deeper. You're talking about forecasting. You're talking about historical data. You're talking about all kinds of number crunching that is way beyond what search is meant for. So I wanted to bring that up because, again, these are all different technologies that are built for different reasons, right? Search is literally for search. And with that, you get your fuzzy matching. You get your your quick aggregates on counts of data. You get your ability to sort and page and do all that kind of stuff. And I don't know that we talked about it that much. You also get scoring, right? So when you have different types of data in your system and you do a search, if you think about this, when you search for something on Google, it's going to come back with what it thinks its top 10 results are based on what you searched on. And it's because it applies a scoring algorithm to the data that comes back based off what you searched for and the types of documents there. Same type thing happens in a search engine on your side. So if I typed in the word wood on a search engine and I had woodworking as a category and then I had books as another category, it might come back with a 90% score on the woodworking category and a 60% on the book category, because it's going to find things in both, right? So you get those kind of features. You're not going to get that with an OLAP cube. You're not going to get that in a data warehouse because it's not what it's meant for. Just like in a cube, you're going to get all these slicing and these dimensions that you can just break down in tons of different ways. They are tools that solve different problems that can all work in conjunction with each other to get you what you want as a full suite of products, but none of them replace the other.
It sounds like, to say it another way, is there's a lot of overlap between these different products, but ultimately, cubes are kind of designed for reporting and search engines are designed for searching. So it's just a matter of, using a specific tool for a specific job.
Yeah. I mean, in a nutshell, that's it. And that's the thing, right? People have done crazy things with relational databases because you can. But does that mean you should? Probably not. You can accomplish a lot of things by being creative, but these tools, what you said, they're very good at doing specific things that can really help you out in those areas. You don't have to use them. They have different use cases. But, you have any thoughts on any of that?
No, I kind of got lost, like, as you were talking, because I was thinking about, like, just the data warehouse concept and, not having a ton of experience with them, though. I was like, well, I never really envisioned that you would directly use them in an application, like an e-commerce type application, like with the Amazon example, right? I was like, that feels like the wrong use for the data warehouse, but maybe I'm wrong. And there is someone that uses that for that, but then it kind of goes along with what you were saying too about, like, well, you could make anything, there's a lot of overlap to Joe's point. So, you could get away with something whether or not it's the right thing for it or not.
I mean, usually data warehousing is where all your data ends up landing after your transactional systems have gotten the data in. And it's typically for reporting purposes or for people to be able to do analysis or forecasting based off that data, right? So it's like, nowadays they talk about data lakes and stuff like that, but it's usually a place that people pull from to make business decisions off of, not to use in a real live app like what you're talking about.
Yeah, I mean, I kind of view the data warehouse as like a hub and spoke model, right? Like you have spokes of smaller databases that feed into the center, which is the data warehouse. But then there's also other spokes that are pulling from that center that are creating their own little data marts for their own purpose. And that's kind of the way I've always envisioned the data warehouse. Like I never envisioned that you would try to create an e-commerce site that directly access the data warehouse.
I would agree, e-commerce or other. And that's the thing. I mean,
well, it's just following along with our Amazon example.
Yeah, no, that's totally accurate. And the thing is, again, you could make it to where it does something like that, but I don't necessarily think you'd be solving the problem the best way, right? If you have a search problem that you're trying to solve, then a search engine matches that thing. But no, you are going to ETL that data into that search engine in a very denormalized format so that the search engine can do what it does well, right?
One point, though, that I don't know that I heard, maybe you made, but about like fuzzy searches or stemming, word stemming. Like those are features that the search engine is going to provide for you that any kind of relational database system you're not going to get.
Well, you can. So
not easily for free.
Well,
it's not baked in as a core concept. Like, you can do a lot of stuff with full text search, and a lot of different vendors have kind of added some of those features. So, there's pretty much anything you can say about any tool. Someone can come and say, oh, there's a checkbox for that and whatever. It's just a matter of how core that functionality is to the center of that tool.
Yeah, stemming might not be a part of it. I'm not aware of that in like something like SQL Server, but I know the full text, like find words close to this and all that. You can do a lot of that.
Gray being like, with an A versus an E.
Yeah. And I can't remember. It seems like I looked some of that up, and there might be a little bit of that that's available. But generally speaking, yes, it's not as full baked as the other ones, right? And again, it's just picking the right tool for the job. And that's why I wanted to bring it up. There were several questions like, why wouldn't you just do this? Or why wouldn't you just do that? And none of them were like attacking questions. I think it was truly like, yo, why wouldn't you? And hopefully we answered some of those.
Yeah, that actually lines up really nicely with the topic tonight, because we're going to be talking about a lot of different algorithms, and a lot of them ultimately do the same thing. Exact same inputs, exact same outputs, but there are strengths and weaknesses in this, even in this very limited topics, that would lead you to pick one over the other.
So let's use that as a segue to dive right in, and let's talk about these algorithms. So we're going to be talking about some of the algorithms that you should probably already know, and if you don't, then this would be a good one for you. And one question is like, well, why do I need to know these algorithms, right? So kind of as I hinted at before, if you ever do any interviewing, these are certainly going to come up in some way or form. Like you might accidentally implement one of these and not realize it, and then they're going to start asking you about the complexity of it. You need to understand the complexity. That's another reason why we need to talk about these, so that you can know when or when not to use them. And aside from that, you probably aren't going to find a need to implement these yourself, because whatever framework or language that you spend your daytime in, your day job in, is probably already going to have these, or better implementations available for you. But remember that first point that I made. So you should actually start practicing how to implement these and others, because if you do get asked in an interview, like, hey, how would you sort this? Or how would you implement this particular algorithm? You're going to want to know. So let's dive in with the first, maybe the easiest one, and that is the bubble sort.
And do we want to mention we got these algorithms from the simple algorithm section of the Imposter's Handbook, which is a book that we love.
Yep. Hey, and before you dive directly into the bubble sort, I will say, being somebody that interviewed people at one of the large tech companies, these things come up a lot. How would you do a binary tree search, or how would you do this, or how would you do that? It is something that if you're going to work for one of the big tech companies out there, the Microsofts, the Googles, the Amazons, these are the types of things that you will get hit on.
Yep. So let's go into the bubble sort. First, starting with like, well, what is it? So there's going to be several of these algorithms. So I'm going to try to answer like a couple, some core questions. So namely, like, what is it, right? So we're going to iterate through a list that needs to be sorted, and we're going to compare adjacent items, swapping them if they are in the wrong order. And we're going to continue this process until there are no more swaps required. So let's consider we have a small list of 5 items, all right? And those items are in the following order: 1, 3, 5, 2, 4. Okay, so we're going to start walking through this list, and we're going to compare the 1 and the 3. They're already in the correct order, so we move on. Then we get to the 3 and the 5. They're also in the correct order. Then we get to the 5 and the 2. This is the first time we found something that's not in the correct order, so we're going to swap those. So now our list is 1, 3, 2, 5, 4. Right? Then we'll compare the 5 and the 4. So the 5 is getting compared a second time to an adjacent item, and we discover that we need to swap it. So now our list is 1, 3, 2, 4, 5. Okay, so we've gone completely through the list, and we're most of the way there. We had to compare one item a couple times, but we're not done. So we got to go back through the list again. So we're going to keep walking through the list, 1 and 3.
Started at the very beginning, like node 0.
Yes, element 0 of the array. Yes, we're starting from the very beginning. So our 1 and 3 are still good. Then we compare the 3 and the 2. Now we need to swap those. So those are going to be swapped. So now our values are in the order of 1, 2, 3, 4, 5, but our comparisons aren't done. We still have to go through the remainder of the array. So we still have to compare 3 and 4, and then 4 and 5, and then we're done. Then we have to go back through it again just to verify that there is no additional value that needs to be swapped, right? So we went through that 3 times to go from 13524 into 12345, right? So that's the bubble sort in a nutshell. You're just bubbling the values, like in that kind of, you're bubbling them into the correct order, but you're doing them in a very kind of slow pace, I guess you might say, like one at a time kind of comparisons.
So you just keep swapping neighbors until you don't need to swap anymore.
Correct. So what are the strengths of the bubble sort? So probably the best one to say would be its strength would be that of all the algorithms you might ever hear talk about, this is going to be the easiest one to implement and certainly the easiest to understand, right? So you can make a case that because this is so easy to understand and implement, that it makes it a very nice introduction into other algorithms, right? Although there are some that argue that other algorithms like an insertion sort or a quicksort should be used as the introductory algorithm instead of a bubble sort. But at least academically, I feel like bubble sort comes up first just because it is kind of easy to talk about and kind of wet the palate and give you a taste for it, and then you can move on from there. So,
it's not so bad when the list is already sorted.
Yeah, if the list is already sorted, sure,
one
fine.
run. Yep.
Also, I kind of like that as an example of what not to do. So a lot of times in like computer science class or in interviews, if you find yourself doing something that looks like a bubble sort, meaning you got like a for loop and you're looking at everything twice, and then you're like, this kind of reminds me of the bubble sort algorithm. Chances are there's a much faster way to do it, and it's a trick question.
Yeah. So, kind of going along with that, what are the weaknesses of this algorithm? So, somewhat, I guess Joe might have hinted at it, like this might be one of the worst sorting algorithms that you could pick in regards to complexity. It's horribly inefficient, as you saw just in that 5 element array. We had to go through it 3 times to get it sorted, right? So there's almost always a better choice than the bubble sort, especially for like large lists. I mean, you can maybe make the case that if your list is rather small, then maybe it's not that horribly inefficient and it's okay to use it, right? Maybe you can make that point, but usually there's something better that you could choose. Worst, and then this was I found curious that according to Wikipedia, the worst case and the average, which I questioned, like, and the average time complexity for the bubble sort is O of n squared. So if we remember our big O complexity, you can head to bigocheatsheet.com. That one is not one of the worst offending hockey sticks, but it's really close to the worst offendings. Like, it was like third worst, in terms of complexity, time complexity. So, and kind of to Joe's point a moment ago, like you saw that we were nesting over this same thing multiple times. So, that's almost always going to be a sure indication that you're heading into O of n squared territory.
I was trying to think of like a real world example where you might do something like a bubble sort. And I was trying to imagine like a teacher, like say an elementary school teacher, and they've got a stack of test scores, like tests with grades on them. And they want to get them in order, right? From like worst score to best score. And with bubble sort, what you do is you take that stack and you compare the first paper and the second paper. If one's bigger than the other, you flop them. And you do that through the whole stack. And then you start back at the top of that stack and do it again and then do it again and do it again. So you can just feel kind of intuitively like you're going over the same data over and over and over again. It feels wrong.
Yeah, I did try to find some like real world uses for the bubble sort because I was curious, like this thing has to have more value than just academic use, right? And it was I really didn't come up with anything of interest. There was a case that in the Wikipedia article for it where it talks about like there's a very popular use that is very specific for graphics, but it really felt like, aside from that though, you should pretty much avoid using the bubble sort in real world, aside from being asked about it on a job interview maybe. But otherwise you should try to stay away from it in like your day job, right? But in the case that Wikipedia was talking about though, it was basically saying like, hey, if you can assume, which is a strong assumption, but if you can assume that the list is already almost sorted, then the bubble sort performance isn't so bad, right? Like it will be okay. And there is this one quote in here that I wanted to call it, see what you guys thought about it, where in the Wikipedia article for it, it says, in computer graphics, bubble sort is popular for its capability to detect very small error, like swap of just 2 elements, in almost sorted arrays and fix it with just linear complexity. For example, it is used in a polygon filling algorithm where bounding lines are sorted by their x-coordinate at a specific scan line, a parallel line to the x-axis with incrementing y, their order changes. 2 elements are swapped only at intersections of 2 lines. So like that last part of it was like, okay, I thought I was kind of following you, and then you got into the polygon filling algorithm part, blah.
And it looks like it has to do with the actual like scan line. So maybe like wanting to sort things in a way that like visually makes sense with that use case.
Yeah, I mean that's where it was like, I don't know. I kind of thought like their example got a little too much into the weeds for me, but that was about as best as I could find for a real world use case for the bubble sort.
And you imagine that like the worst case scenario is also when the data is sorted just in the wrong direction. If you've got 10 with 9, 8, 7, 6, that means you're going to have to march that 9 all the way over to that last spot.
Yeah, and that's that's going to be ridiculous.
Yeah, and I think that wraps us up for Bubble Sport.
Yep.
You guys play that Bubble Sport where you get those things in the packages and you pop, pop, pop?
That's right.
Yeah, that's actually awesome. Bubble Sort is not awesome. But what is pretty awesome, I got lucky here. I got Merge Sort. And Merge Sort is probably the most common type sort. So if you're just doing something in a library, and there's a good chance that it's going to be doing some sort of merge sort. I don't have any hard numbers before that for that, so maybe that's not true anymore. We've got some other algorithms that are pretty cool too, but this is like a good standard. And it's a divide and conquer kind of algorithm, which is pretty interesting. It's a type of problem where you keep splitting up your input, and then you kind of bring it back together. And while that sounds like kind of at a high level, like you're not really doing anything different than a bubble sort where you're just kind of looking at smaller pieces and then putting it back together, and it actually ends up being much more efficient because you don't have to keep relooking at the same amount of data or the same data over and over again. And so the way it kind of works is with that, using that teacher example, you've got a stack of graded tests, and you split that stack in half. And then you take that left stack and you split it in half again. Take the left stack, split it in half again, split it again until you're down to 2 papers. And you basically take those 2 papers and then you sort them, go back up a level. Now, if you've still got papers that need to split, you do that again. And eventually you're going to get to the point where you've got like 2 papers in your left hand and 2 papers on your right hand. Both of those are sorted. And that's really the key there, is that the papers in your left stack and your papers in your right stack are both in order. So what you can do is, rather than comparing each element to each element, is I'm not going to try and describe it too well, but basically what you can do is only go through each item once. So you say, left one, are you greater than the item on the right? If yes, then the right one goes in first, and then you repeat. And the opposite, if the whatever the opposite of what I said was, if you basically it changes how you return. So what that means in practice is you split your stuff down and you build it back up. But because you know that the lists are sorted on the way up, you don't have to keep recomparing the same values over and over again. Like the example where you've got like 1 through 10, but it's sorted 9, 8, 7, 6, 5, all the way down to 1. You're going to compare 9 with 8 more than once. You're going to compare 9 with 7 more than once, 9 with 6 more than once. You're going to keep doing the same work over and over and over again. But just the simple act of only comparing these sorted smaller lists makes all the difference here. And that is going to bump us into making it an O of n log n, which is kind of the standard for sort algorithms. I also wanted to mention that they call it a stable sort, which means that, I don't know if we want to go into this, but it's basically the idea is like that if you sort this list twice with merge sort, then you're always going to get whatever item came first in a match. So if we've got two students that got a 78 on the test, you're always going to get the one that you ran into first. The one that was leftmost in your data set is going to be sorted in the first position, which in terms of numbers, it doesn't matter because a 78 is a 78. But for some reason, you're doing something where you do want to see that first value in the array is being sorted higher, or rather, maybe you just want to make some decision, maybe you want it lower, then this would be a good algorithm to use because you can make a deliberate choice on what happens when you see a match. And what else? So
space complexity on these. So
yep.
Just real quick, I thought it would be worth mentioning again, borrowing from the big cheat sheet and bigocheatsheet.com. The bubble sort space complexity was O of 1, but for merge sort, it's O of n.
Yep, and the deal with that is because in bubble sort, you don't need a new array. You could do everything in place. You just swap the values of the indexes. So that's really easy. You don't need a new data structure there. It's just whatever your input is. Merge sort is different. When we break stuff apart, actually into smaller and smaller arrays, you don't actually need to create separate arrays for that. You can actually just kind of keep track of your start and end indexes. But when you start putting things in order, building that array back up to return, you have to do that. I'm sure somebody's figured out some convoluted way of doing it without, but for the most part, you have to do it in a new data structure because it's very important that you keep those lists in their individual sort order when you're building this thing back up. And so you do end up having to create another data structure that is exactly as large as the one you got in, which is, this sounds terrible, but actually works out really well and to its benefit in some cases where, like, for example, this is a great algorithm to use if your data set is too big to fit in memory, because you keep dealing with these things in smaller chunks. And then eventually when you kind of build this thing up, you're able to deal with it in small parts because you're only ever comparing small things together. And so this is an algorithm that divides nicely up even in distributed environments.
So kind of to say that in another way, in a low memory setting, if I give you an array of, let's say, 1 million integers, then with a bubble sort, while it might not be the most efficient way, you don't need any additional memory to do that sort. But with a merge sort, you will need to create a second array of equal size to the first. So you will have 2 arrays with 1 million integers in it. One is the input, one's the output.
Correct.
Yep. But in a merge sort, you don't have to have both those arrays in memory. Like, it's easy for you to kind of only keep the chunks that are important. And same with bubble sort. I'm sure you can imagine you could throw that thing on disk and then kind of only pull up the 2 individual numbers that you need. And that'd
well,
be
I'm
kind
talking about the case of, like, if you just wrote a function to do the sort, right?
Right.
And it had to return the result, right? That's why I said the input and output. But yeah, I mean, to your point.
Well, think about it this way: you've got like a cluster of computers. You've got 10 computers, and you've got a data input size of like 1 million. You could throw 100,000. You could divide that array up into chunks of 100,000. Give each one of those 10 nodes 100,000 amount of the work to do, and they can all merge sort their individual pieces and then pass up those pieces to some sort of master node that's going to merge those individual parts.
Mm-hmm.
And that's totally valid. Nobody did any extra work. It's still a merge sort. But could you imagine doing that with bubble sort? Like, each one has 100,000. And so it's like the first server does all its work. Now the second server does all its work. Third server, all the way to number 10.
You'd have to do it all when it came back together too.
Yeah. I mean, that doesn't work out very well for bubble sort and being able to do that stuff at the same time. But with merge sort, it's like designed for it.
Yep. Very cool. So the space was O of n, and then it looks like the operations to do it are also O of n. It's got to run basically the number of operations as there are elements.
No, the time complexity for merge sort was O of n log of n.
That's time complexity, but the operation, right? Once we need to sort the items. O of n was the sorting of the items. Yeah, no. So the complexity is in log n.
Yep. And as a solid performer, it's often a kind of default, and so it's a popular choice. And I find an interesting stat. In worst case scenarios, merge sort does about 39% fewer comparisons than quicksort does in the average case. So a lot of how people compare search engines, sorting algorithms is they basically compare them to each other for different types of use cases. And there are some certain cases where ones outperform another one. So this one just overall performs pretty well, but it does have a couple of weaknesses. Mainly one that I think is the weakest point is that it's annoying to program, which is silly because obviously this is the kind of thing that you program very rarely and use very often. But I sat down at Panera today for lunch and programmed it. And it's pretty annoying because you have to kind of split it into two parts. The first part's easy. You basically have to kind of keep splitting down the arrays until you get two individual arrays with like one element in it. And then you merge those guys back up, and then you write a function that actually does the merging. And it just seems like the whole thing is like edge cases and if statements. So it's not a very elegant looking algorithm if you do it correctly. You'd like bubble sort, like I feel like, it's just like a couple of lines and like you can look at it and get it. Merge sort, you're looking at it, you're like, are you sure this is faster? So this looks wrong, guys.
Hey, so going back to this, we said, log in, all that kind of stuff. Any of you want to give just a real quick synopsis, seeing as how these are number things, what log of what means what? Anybody remember off the top of their heads?
It's a whole lot less. So we're generally talking about, is it log base 2?
Typically, that's the thing, right? You have to know what the base is. I think by default, it's usually log base 10. I think. So log of 10 would be 1 because it's 10 to the first. So 10 to the first gives you 10, right? Log of 100 on a base 10 would be 2 because it's 10 to the second power gives you 100, right? And so log of 1,000 would be 3, etc. So now base 2, that would obviously be, whatever it took using that base. So
I'm talking log base 2. So pretty much any time in computer science that we're talking about logarithms, like in time complexity, we're almost always talking about base 2.
Okay. So
which is messed up.
Yeah. So it's worth knowing that because it matters in terms of what you're thinking about, right? So if your base is 2, then we're saying what 2 to what power will give you the next number, right? So log of 2, base 2, the answer is 1, right? If we say log of 4, then it's 2 because it's 2 squared, right? So then log of 8 would be 3, and log of 16 would be 4, etc., right? So it's basically the inverse of a power is kind of what you're getting at, right? So if you go back and put on your math hats, when you had 2 to the second power, or let's say 4,
the eighth, it's 256.
Yeah, and if you wanted to know what the inverse of that was, like 4 to the 1/2 power, that was 2 squared, right? So it's you got to go back to your math thinking, but it's basically the undoing of the powers.
Oh God, I think I just did it wrong. You can fit 256 worth of binary in 8 bytes, but I think it's actually 2 to the 8th is something else.
Well, let's do 256. I think that might be right.
Let me ask Google. Like log base 2 of 256.
Log base 2 of 256 is 8. That's correct.
Okay.
Yeah, because it's 2 to the 8th power will give you 256. So just remember that when you're talking about logarithmic time, you're basically doing an inverse power. And that's why they're so much faster and more efficient, because as your size of your inputs or your operations increase, the amount of time or complexity of whatever is going down by a factor. And that's why log, when you talk about log n, that is why that's so much better, is because as your size is increasing, your actual operations are going way down, or your space or whatever you're talking about, your complexity or your that is going to go way down. So,
when I was at Panera today, I actually did a little example where I programmed bubble sort and then I programmed merge sort, and I ran them both. And bubble sort with just a random array of like 1,000 entries, I ended up doing 966,000 comparisons and 246,777 swaps in a sample run. That's every time we change the numbers, and for only 1,000 items in the array. And you can tell that it actually did pretty well, because that's much less than 1,000 times 1,000. That would have been a million. And my merge sort did 9,488. So a full 1% less comparisons and 245 swaps.
Wow. That's almost nothing.
Yep.
Well, this is, going back to your logarithm conversation there, I've always thought about, whenever I think about logarithms, it's always, you're talking about measuring magnitude.
Yes.
Like the order of magnitude, like what's the difference? And so, yeah, it's like when you talk about earthquakes, for example, right? And a 4 versus a 5 versus a 6, on the Richter scale for the strength of the earthquake, right? Those are like orders of magnitude different. It's not like it's just one more powerful.
Right.
It's an order of magnitude more powerful than the other one. So that's kind of the way I think about logarithms. I could be wrong.
No, that's probably pretty accurate. I mean, it's almost like when you talk about sound, like decibels, a lot of people don't realize, 30 decibels is like a whisper, somewhere in that ballpark. 40 decibels is double the volume of 30 decibels. 50 decibels is double the volume of 40 decibels. So it's not like it's just going up 10 things. It's doubling every 10. So yeah, it's the same type thing where you get into the powers. And so the reason I brought it up is because it's easy to say, log in or n log in. So I wanted to bring it up because you have to think about these things in mathematical terms, because that's what big O notation is, right? It's all about what is the mathematical operation or complexity of this thing. And so like when you say n log 4, right, we just said it's base 2, that would be 2. But if you said, if it's O n log n, then you have 2 times 2. So your complexity is, O 4 or whatever. So I think it's worth at least knowing when we talk about these things, so you're not just drifting off into no man's land going, oh God, what are they talking about? So,
one thing I noticed is kind of funny about complexity times, if you look at it in the cheat sheets, like anytime you're looking at like an algorithm and says you have the input or you have the whatever, like, there's a log n going to be in that number. It's just expected to write in that blank there.
Yep.
Yeah, I mean, the bigocheatsheet.com is an amazing resource for, anything. Like if you already, all this conversation about O of login or O of n login or O of n or whatever, if any of that's, if you're questioning any of that, you could head to bigocheatsheet.com, and it's a great resource that just very simply, very easily visualizes it for you in a graph. And then they talk about it in terms of common data structures and then sorting algorithms. And there's even like a poster that you can get if you wanted to just hang that on your wall next to your Lamborghini or Ferrari posters. It would be right up there. It would belong. It would fit right in.
All right. So with that, then we're going to get on to mine, the Quicksort, which is a little bit harder to explain just because there's so many things that kind of happen at once. But this is also another divide and conquer strategy. So what it does is it basically takes a list and it breaks those lists into smaller lists, but it uses a pivoting technique. So what Joe just talked about with the merge sort, he just split the lists in half and then sorted within those once it got down to 2, right? Like half until you get to 2, and then you sort those and then you put them all back together. This one's kind of interesting because what it does is it sorts in place, but it uses this pivot. So it kind of goes through the thing where it breaks it apart into smaller ones, and then after it's all done, then everything's just sorted in place. And here's the interesting thing. It says the partitioning is done at random, sort of. And the reason I say sort of is because what they do is you take a list and you take the last number in that list, and this is actually called the Lamoto partition scheme. to where you take the last number in that list or the last item in the list, and that becomes your pivot point. So I'm going to give an example, and this is going to take a little while to walk through. I mean, I'll go as fast as I can, but there's a lot of swapping going on. So with this, the Quicksort, let's say that we have the numbers in a list 5, 2, 7, 4, 1, 8, 3, 6. Now I know that's a bunch of them, but
go grab a pencil.
Yeah, get a pencil, or go to the site when this thing's up, and you can take a look at it, because I'll have it written out as far as what they end up being after each one. So the last number here was 6. So it says you're going to take that last number and you're going to use it as the partition value, and all that means is that's going to be your pivot. So everything's going to be compared to that number as you go through this list. So what it's going to do is all values less than the partition will stay to the left of that pivot point. So anything that's less than 6 is going to stay on the left.
And you don't have to move it because it's already to the left.
It's already in the right spot, or the correct spot. Correct. Because right's going to get confusing. And turn here? No, turn there, turn right. Yeah, it's right. Turn that. No, sorry. Anyways, so all the values that are greater than 6 are going to get shifted over to just after the pivot point. But to do so, that means that whatever number was before the 6 is going to have to swap places with the number that just moved to the right of the 6. All right. So if you think about it like this, if we find a number that's greater than 6, that thing is going to move over to the right of 6, which means it's going to push 6 to the left in that list. So whatever was over there on the left now has to go back to where that other number was, towards the front of the list. So let's go ahead and roll through this thing. So again, it was 5, 2, 7, 4, 1, 8, 3, 6. All right. So the first number, 5, it's less than 6, stays where it is. The second number was a 2. It's also less than 6, so it stays where it is. 7 was the third number in that list. It's greater than 6. So what we said we were going to do is we're going to take that 7, we're going to bump it onto the very end of this list now, right?
Well, you don't bump it on, you swap it, right?
Well, you're basically going to push the 6 over to the left, which the number before the 6 was a 3. So now you're going to move that 3 to where that 7 was.
Okay.
And then you're going to move the 7 after the 6. So kind of what you're doing is you're shifting all the numbers down before the 6, or you're not all of them. You're shifting the 6 down one position, which moves that number that was there back to where the number is that's being pushed out to the right of 6. So now
your pivot point is moving.
Your pivot point is
moving inward.
Yes.
So we started with 527, and now we're at 523.
523, because the number that was before 6 at the end of the range was 3, and that had to move into the 7 position. So now what we had starting was 5274 1836. Now what we have is 5234 1867, because that 7's after the 6 now. So now what we're going to do is we're going to look at the 3, because the 3 just took the 7 spot. So we want to make sure that that thing is in the right position. 3 is less than 6, so it's going to stay there as well. So now we're going to take a look at 4. 4 is good. That stays there. 1 is good. It's less than 6, so that stays there. The next number on the list was 8. 8's more than 6, so we're going to do the same little dance move, right?
Oh, going too fast, man. Hold on. Write my pencil down.
So
pencil sharpener.
So now what we're at right now is 5234 1867. So we compared the 4 and the 1. Those are both less than 6, so those didn't move. But that 8 right before the 6 now, that is obviously more than 6. So we're going to move it to the right of 6. Well, conveniently, because it's right next to the pivot point, all we're going to do is swap these, right? So now what you've got is 5234 1687. All right, so that's the end of the first partition sort. So now what we're going to do is you sort of take 6 out of the equation now. So now really what you've got is you've got the list to the left of where 6 ended, and you've got the list to the right of where 6 ended. So on the left you have 5, 2, 3, 4, 1, and then 6 is your partition point. It is where it's going to be at the very end because of this little dance move that we just did. To the right now, you've got 8 and 7. So we're going to go through these lists individually and break these down. So
And my first inclination is to think like, okay, move the pivot over, start over again. But then you realize like, wait a second, we've already got that 6. We've got a divider. And we know that we've got a list on the left that's all smaller and a list on the right that's all smaller. So why don't we just partition sort those two since we know we can do it in line?
Exactly. And the thing is because of how those things moved around, that 6 actually ended exactly where it needs to be for the final result set. And that's the cool part about the way this thing shifts around. So with 5, 2, 3, 4, 1, you have to pick a new pivot point on that left list, which the last number was 1. So that's your pivot point. So this is where it's going to be kind of interesting. So the first number 5 is obviously greater than 1. So you're going to move that to the very end. And so now you've got, and because you did that, the number that was before 1, which was 4, is going to take the place where the 5 was. And I know this is confusing as heck to listen to, but now you've got 4, 2, 3, 1, 5. You're going to do the same comparison now. Because 4 moved into that first spot, you're now going to compare that with 1. 4's greater than 1. So
we're not doing anything different. And this is the same rules. We're just kind of applying them and kind of drilling down.
Yep, you just keep going. And so now because you move that 4 into that first position, you're going to compare that one again. 4 is greater than 1. It's going to go to the right of the 1. The 1's going to shift down. And now 3's in the first position. 3's greater than 1. You're going to move it after the 1, shift the 1 down. And now 2's in the first position. So this is really cool because this is actually just sorting the list all the way down, and you end up with 1, 2, 3, 4, 5. Now, on the right list, we had 8 and 7. This one's really easy. The pivot point is 7. The first number is 8. 8 is greater than 7. It's just going to swap places with the 7, and now you have 7 and 8. And then you put these lists. These lists are now in the correct order. They were sorted in place because they were just shifting and moving things around. So this is all done, and it was done pretty well. Now, it's kind of confusing and hard to look at. So let's talk. I didn't break these down into weaknesses and strengths like they did, but hopefully I'll be able to summarize this pretty well. So here's what's interesting. If your list is already sorted and you take this approach, it is horrible performance because you're going to take these pivot points and you're going to go through all of them, and you get to O n squared time on this thing because it's going to basically shuffle everything to put them back in order. So that's kind of an interesting thing to know about it.
It'll shuffle everything?
Yeah. So if you think about it, if you have 1, 2, 3, 4, 5, 6, it's going to make 6 your pivot point, and so now it's going to compare 1 to 6. So now
in order. It's not going to shift everything. It's going to have to keep moving the pivot.
It's going to have to keep it. So 1, 2, 3. It's going to go through all of them. Why? Hold on a second. No, that 1, 2, 3, 4, 5.
Am I missing something?
Hold on. Oh, well, you still got to go through the list.
Maybe you're thinking if it was reversed.
No, they said in order. If it's all sorted and it's already sorted, you have to have a pivot point, and then, why would that be? Now I'm not so sure because it seems like it would be O sub n, not n squared. I'd have to go back and look at it now. I read it and blindly trusted it. Any thoughts there, Joe?
Trying to look it up. It doesn't make sense to me, just like you guys said, I would think that the worst case scenario would be reverse sorted because you would immediately you keep swapping that.
You'd have to keep moving
worst
it
number of times.
Well, I have the link.
Yeah, I mean, I do see that in the book. Again, this is the Imposter's Handbook where he says that, if it's pre-sorted, we'd have to split and order the list for every element, turning the complexity into O of n squared.
Yeah. And thinking about it, like you said, the 6 is your pivot point. Unless you're moving something to the right of 6, I don't see why that would happen. And I actually can't.
Is it because
I think it's because you keep moving the pivot.
But
right?
You don't move the pivot, right? Because you never swap it, but you still have to compare with every other operation. So it's not about the swaps. It's like in your array of 8 there, you do 8 with 7, 8 with 6, 8 with 5, blah, blah, blah. Then 7 with 6, 7 with 5. So you literally compare every number against every other number. And that's where the n squared comes from.
Okay. I'll take that.
No. But wouldn't you still have to go? Am I thinking of this wrong? Maybe I'm thinking of this wrong. Because I was thinking if you had like a 5-element array, let's just talk 1, 2, 3, 4, 5.
Mm-hmm.
Right? So 5 is your pivot point. You have to compare 5 to all of the first 4 numbers, but it doesn't necessarily, you don't know yet that your other 4 numbers are in order.
Right.
So now you got to pivot. You got to use 4 as the pivot because it's on the left of the 5. So you got to use 4 as the pivot and find out that everything's in order. Now you know that 4 is in the correct place, but you don't know about the first 3. So you got to go to the left, everything on the left, because everything on the left isn't sorted yet. So now you have to go to 3 as your pivot. So you keep moving your pivot point, and that's where the O of n squared comes from.
I don't think you do that moving though. I think it's all about the comparison. I was able to finally find somewhere to verify that the worst case scenarios, there's actually 3 of them. One is when the array is already sorted in the correct order because you have to compare all of them. Another is when it's sorted exactly wrong. And that is because you have to compare everyone against each other. But in that case, you actually end up doing that swapping too. It's just that the swapping isn't such a big deal compared to the actual number comparisons, just because there's so many more of them. And the third case is actually if all elements are the same. Like if you've got an array of all 5s, that's also worst case scenario because in that case, you're also comparing every number against every other number.
Okay, so it's just in the comparisons that you're getting that. Okay, that makes more sense. Yeah, because I don't think the pivot point would ever move at that point because you don't have anything to swap.
And kind of like intuitively, like swapping is more work. So it's kind of like tempting to think like, okay, that's a problem. But really, when you're looking at algorithm complexity, it's all about how it scales. And so it doesn't really matter that the operation takes a little bit longer to do. It's all about how many times it has to do operations.
Okay.
Wait a minute. How am I missing this then? It would have to, the pivot would have to move.
No.
In the 1, 2, 3, 4, 5 example, they're already in order.
Mm-hmm.
Your 5 is your pivot.
Mm-hmm.
You compare 5 to the first 4 numbers, 1, 2, 3, 4, 5.
Mm-hmm.
And each one of those numbers is already less than 5, but you don't know that they're in order. You just know that they're less than 5.
Right. So
you have this list on the left that is now 1, 2, 3, 4 that you know is less than 5,
that you're gonna have
but
to
you
run
still
through
have to
again.
go through and sort that. So you have to move the pivot.
Good
so
point.
the pivot point moves.
Oh, I see what you're saying. Yeah, you have to move the pivot. You don't have to swap the pivot.
That's why it's O of n squared, because you have to, your pivot point becomes everything from the list backwards.
Okay, that makes sense. Okay, so you're not moving your pivot. You're choosing a new pivot after each run.
Okay, however you want to refer to that.
Yeah, when you said move, I was thinking swap.
That's what I was thinking. I was thinking swap too.
It's not swapping. I just meant you're picking a new pivot point for every number.
That makes perfect sense. And yes, that is exactly what you'd have to do, because what you were saying, you wouldn't know that they were sorted until you step through every single one of them.
Yeah.
Okay. So here's an interesting thing. So the take on it is typically you choose the last number in the series to do this. There's another approach to this that can make it better in most cases, where you try and get smart and you try and pick a median, right? Which means that you would have to scan the list one time to find out what all the values were, and then you'd have to pick the one in the middle, right? Or an average or whatever's closest to the average. Then that way you sort of divvy up your list into an even on the left and an even on the right when you choose an intelligent pivot point. But that does require an additional step up front without just jumping directly into the algorithm. But if I remember right, this one, man, I could have sworn I put the big O on this one.
So if we knew we had a normal distribution, then this would be a great choice, because we know that things are mostly going to sort out, assuming it's like randomized nicely, it's going to be a great choice. And it also seems like, the worst case scenario we said was O of n squared, which is much worse than, and that's on par with, that's bubble sort. But it's much worse than merge sort. However, I'm guessing that in like the average real world cases, it ends up being much faster and performing much faster than merge sort. Otherwise, we would never even talk about it.
Yeah, it says in the best case, it's O n log n. So it's somewhere in between O of n squared and O of n log n. So, it's probably not terrible in most cases.
Yeah, but you can kind of see why like merge is the kind of the default there, because it's like, well, we've got one algorithm that is sometimes faster and sometimes much slower, and we got another one that's always pretty good.
Right.
Yeah, I mean, like space complexity for merge sort, best, average, and worst were all the same O of n log n. Yeah, but to your point, like Quicksort goes from one extreme to the next.
But there is the space thing though, right? So that's where the merge sort is actually a little less efficient because it's going to require double the memory footprint.
Yeah, this is where the magnitude comes in.
Yeah, so depending on what you're doing here, this is sorting in place, right? This is just shifting out elements in the array or whatever, whatever memory thing that you've got. So your space is constant, but your actual operations could be pretty bad.
Wait, constant?
Or the fix, it'd be O of 1, right? The same. Whatever the input is, it's the same.
I think that sounds right, but it's curious because I have the big O cheat sheet here in front of me. That's why I sound so smart. And, and they actually show the space complexity. Oh, no, this is the worst case. I'm sorry. Worst case for Quicksort, they show the space complexity is O of log n.
Huh. Why would it be less? That doesn't make sense.
I don't know. I'm with you. I think that it would be similar to the bubble sort where it would just be O of 1. That seems reasonable.
The only thing I could think, the only reason I can think that you would have a log, and I'd probably need to look at the code, is my guess is you're probably going to have a variable to store the swap values, like 1 or 2 variables there, because as you're shifting things, you might need to move something into a temporary store to push it out. I don't know.
That shouldn't factor.
Bubble sort, though.
You could do math. You could do math. I mean,
constant variables like that should drop out of the equation.
They're not supposed to matter, right? Yeah.
But you got to wonder too, like all this stuff, like really depends. Like looking at Quicksort, even there's like different ways of doing it, different ways of choosing the pivot. There's even a stable Quicksort and a non-stable Quicksort, and so you can imagine that, like if you're, big O cheat sheet, like you might be able to construct a situation with one version of this algorithm that somehow ends up looking like this. So it's really hard to know exactly what their qualifications are and which implementation of the algorithm they're using to score.
Yeah, man, I'm not real sure why. Yeah, anyways, it's mostly shifting things around within the arrays, so that's kind of odd. But anywho,
yeah, I'm curious about that too.
Yep.
Yeah, there's another great resource. I'm going to have a link to this one. This might be one of my favorite resources that I've come across here lately. But I want to say that you can get to it real quick. I'm going to double check it. If you go to sorting-algorithms.com, and it'll redirect you to the real one because it's a really long name. But it has like all these great animations for all of the different sorts. And you can see like how, for example, a Quicksort works on a random list, a nearly sorted list, or a reverse sorted list, or a list with few unique items, right? And you can see like all these animations comparing to one another, or you can see how one sort works for all of those variations of the data. But you can also go and dig into any one of those and see the details of that sort. And so, for example, there's Quicksort, but then there's another version of it, which is instead of the 2-way partitioning that Alan described, there's another version for a Quicksort where it's a 3-way partitioning that they get into. But even in the Quicksort here, they're saying like the space complexity, the worst case space complexity would be O of log n. Same as what Big O had.
Yeah.
So, all right. Well, guess we didn't answer that.
Well, so let us know in the comments there. We'd love to see that. And also, if you have any resources for somebody who maybe learned about this stuff like 15 years ago and is now kind of forgetting, but they don't want to like start from zero, let me know. I mean, let us know.
It's funny. Some of these things I literally have not seen since college. Right? Like it's been a while.
My computer science 1 course, like it felt like all we did all year was just talk about like the 4 main sorting algorithms that we're going over right now.
Yep.
So I've done all of these at least once 15 years ago.
All right. So what we got next?
All right. So I got the luck of the draw with the great algorithm. So selection sort is next. So what is the selection sort? So you remember when I said that the bubble sort might be like one of the worst sorting algorithms that you could you could ever use? Selection sort.
Obama even knows not to use bubble sort.
right. So all right. So maybe it's not, this might not actually be the worst, maybe, but this is how we might actually think about sorting something. So it's kind of easy to think about this one in our head. So let's take playing cards, for example. Like if you had to sort playing cards in your hand, like you're playing poker with somebody, like selection sort might be how you might sort those cards in your hand. We're like, okay, let me find all of the, the twos, then all the threes, then all the fours, and try to put them in order, right? So we're going to iterate through the list, finding the smallest element, and we're going to swap it with the first element. And we're going to repeat this for each element in the list. So let's consider the same list that we had with the bubble sort: 1, 3, 5, 2, 4. Okay. So we're going to scan the list looking for the smallest element. And we find that it's the 1, and it's already in the correct position. So we're going to scan the list again, looking for the next smallest value, which could still be a 1, but in this particular example, it's not. So we're going to find the 2, and we're going to swap it with the second item in the list, which was a 3. So our list went from 1, 3, 5, 2, 4 to 1, 2, 5, 3, 4. Okay. So we're going to scan the list again, looking for the next smallest value, and we're going to find the 3. So now we're going to swap the 3 and the 5. So our list now goes from what was 1, 2, 5, 3, 4 to 1, 2, 3, 5, 4. And we're going to scan the list again, and we're going to find that the next smallest item is the 4, and we're going to swap it with the 5. So now our list went from 1, 2, 3, 5, 4 to 1, 2, 3, 4, 5. All right. So we iterated over this list of 5 items 4 times.
So you've basically you're keeping a pointer to the next index that you're going to swap out, and then you're keeping track of the last or the biggest number that you've swapped at that point, or the biggest of the low numbers that you've swapped. Okay.
Yeah, but keep in mind though, there could be you could be sorting things with that. The same value could be repeated multiple times, right? So. All right. So what about strengths for the selection sort? All right. So doing a selection sort, you can just write a simple loop to do a selection sort. So that's great because it doesn't require any recursion. And anytime we ever think about recursion, we should immediately have some alarm bells that go off in our head, because we should think about the data that we're going to be recursing over, because we need to be concerned about Stack Overflow exceptions, right?
Unless it's tail recursion.
Anytime when we recurse, like all of those variables are staying on the stack, right? And as we go into the next iteration of that function. So that's one thing to consider. Now, here's the interesting thing. Wikipedia, according to the Wikipedia article for the selection sort, claims that this usually outperforms the bubble sort. But if you were to look at the Big O cheat sheet, they're ruling on the time complexity of selection sort versus bubble sort, and the sorting-algorithms.com animations that I mentioned, they would lead you to believe that bubble sort outperforms selection sort. So your mileage might vary, but Big O cheat sheet ranks selection sort best case at O of n squared, and it's O of n squared for its best case, its average case, and its worst case.
Nice.
So,
well, it's consistent.
It is. It's got that going for it. It's much like the merge sort in that value. So I'm not.
It also sounds stable.
I'm really not sure where the Wikipedia article, what their meaning was then for saying that it would outperform the bubble sort then. But so this would be a good choice for a small list. And aside from that, there's like Joe said, merge sort will probably be that's going to be your default go-to, right?
If you're a computer. Well, I'll tell you, if I'm sorting something, no matter what it is, this is what I kind of do. If I'm sorting socks or really sorting magic cards or Pokemon cards, right? But color and then cost, like that's where I would do this kind of sort. I'm not merge sorting or merge conflicting.
Merge sort your Pokemon.
I know I should, but no way.
I beat you all the time.
Yeah. It's like I can't find my strong stuff.
All right. So one advantage to this algorithm, kind of like Joe hinted on with it being stable, is that, in circumstances where memory is limited, then this isn't a bad choice, right? Like the bubble sort, its space complexity is O of 1, right? Because you're able to just, swap things out in place. In regards to its weaknesses, though, also similar to the bubble sort, it's not efficient. It's not a very efficient one. Like I said, its worst case time complexity is O of n squared. And it's pretty much like it's always time complexity is O of n squared, best, average, and worst. And we have to scan each element in the order in order to find the smallest value for each position in the list except the last one, because the last one is going to be assumed to already be in the correct place. So this is not a good choice for large arrays. I wrote that, and now I'm trying to remember, why did I write that? That the last position doesn't have to be. The last position can be assumed.
Well, it kind of makes.
Why did I write that?
Or does it? Yeah, because once you get to that last position, there should be no more swapping at all, because it's either going to be equal to or greater than the value before it, I believe.
Because it's not the lowest value because that was the first step, right?
Right.
I'll rethink that. So when to use the selection sort? So
playing rummy?
Playing rummy, yeah, exactly. So if you're playing any kind of card games, this would be a good choice. Which kind of to that point, this is good for small arrays. So, if you're playing a card game, right, you're only going to have a handful of cards in your hand. So, that makes it an easy, kind of relatable analogy there. So, but then the question is, well, how small is small, right? Like how many items in your list is still considered small? So some of the things that I read, people would argue that hey, if you have 10 to 20 elements, then that's small and selection sort will be okay to use. Others would say 20 to 30. So, yeah, guess use your best judgment, maybe.
Yeah, if you have the AMD Threadripper 19, whatever, you're probably fine.
Well, speaking of probably fine, the best sorting algorithm you can use 9 times out of 10 is just whatever your programming language does when you do dot sort.
That's what most people do, right?
Now, here is a very interesting advantage and when to use kind of strength about the selection sort, though. So earlier in the conversation, Joe had mentioned well, hey, with the merge sort, if you're going to write this out to Flash, or if I'm going to spread this across some kind of distributed load or whatever, depending on what my write medium is, maybe it's not as simple as just hey, give me a function that takes in an input and returns an output, right? So if maybe what you're trying to sort is being written to Flash memory, then as you're doing this sort operation, then the selection sort is actually a good choice because it results in fewer write operations, which for Flash memory would be important because every time you write to that Flash memory, you're degrading its life.
So that's interesting. Yeah. In this case, you'd be trading IO for operations, but that might be preferable because of the bubble sort. You could be literally just constantly swapping all the way up it, right? So
yeah,
that's interesting. There are use cases for it.
Yeah, it's funny about bubble sort. It's you will literally march just about every number. If it's reverse sorted, it will march almost every number to almost every position.
Yeah, it's going to write it. You have 10 of them. It's going to write each one of them that in its position -1 total, right? All the way down. Whereas this could it'd be like if you had 10 cards, you'd have 10 swaps and that'd be it. So, yeah, that's pretty cool.
Yep. So moving on to Heapsort, I want to take a brief interlude just to mention why I keep bringing up stability. Stability may seem like kind of a weird outlier that no one really cares about, but actually in practice it has some really cool implications. So when you think about that the magic card example where I've got like a big shoebox full of magic cards, right? Let's pretend that I've got them sorted alphabetically. And at some point I realized, you know what, that's kind of annoying for building decks. So I would rather have them sorted by mana cost. So that's going to be some sort of number. So if I use a stable sorting algorithm on those magic cards, which means that they're going to reliably end up in the same position that I ran into them, then what that means is my output, when I'm done, that shoebox is going to be sorted by mana cost and then by name. If I use a sort that isn't stable, then there's no guarantee. So I'm going to end up with them sorted by mana cost and then nothing. So if you, for example, if you're doing something like in a SQL database or you're building a relational database because you're crazy, then you want to build
those aren't real things in the world. I hear.
You want to order by this and then order by that, and then you want to reorder it or do something like that. Then you're going to want to consider a stable sort because you're going to be able to maintain that secondary order without doing any extra work. So that was my side note. Sorry.
Cool.
Heapsort, that's what I'm talking about. Heapsort is another sort algorithm where this time you're going to basically divide your input into a sorted and unsorted region, which kind of sounds a little bit like Quicksort, where we're going to start with this big unsorted region, and then we're going to kind of lop off a small part of that array or input, and we're going to say this is the sorted portion. We're going to start with just one item. That's the only item that's in order. And then as we go along, we're going to keep plucking items out of that heap, and we're going to be inserting it in order into that sorted region. So over time, the sorted section is going to get bigger, and your unsorted heap is going to get smaller. And this actually looks really cool on those display that website sorting algorithms, because you can kind of see it kind of all like builds one side at a time, and it eventually like overcomes the chaos. It's quite beautiful. But what I want to mention specifically, when I say heap, I'm talking about a very specific data structure. I'm talking about a certain kind of tree where, depending on if it's a max heap or a min heap, the parent is always either greater than or less than its children. And so for a heap sort, there's like a million different ways to do any of these things. But the way I'm mostly going to be talking about is a max heap, where we're going to have the children be always less than their parent. So what I'm going to do is basically take this unsorted array. I'm going to take the first node. I'm going to grab the second node. If it's bigger, it's the new parent. If it's smaller, it's going to go as a child of the root node. And I'm going to keep doing that until I build it up. And what that means in practice is that when it comes time to getting the biggest node, I always have it. And the rest of my heap, while not sorted, is pretty close. So this is like a cool take on the algorithm, where step one is create this heap, which actually gets us close to sorted. And then we kind of let the other half of the algorithm kind of take over, where we do, it's kind of like that, what's it called, selection sort, where you've got, a small number of items and you just say, hey, pop this guy in the right position, and then do it again. And every time after you pluck the root node off of the max heap, you do have to do a little shimmy on the rest of that heap to make sure that the top node is again in the top position. But you only ever have to look at two children. So you don't have to look at that heap and keep resorting over and over and over again to find that max node like you did in selection search. You always know that it's always one of these two values. Does that make sense?
Keep going.
All right.
I'm trying to picture some of it. Yeah.
So the deal with the max heap data structure is that you always know that your root node is the biggest node in that heap. It's always the biggest.
Okay, so if we're looking at a top-down tree node, like a binary tree looking thing, right? But
yep.
This is going to be a heap. Your biggest number is at the very top.
Yep.
So if you had, I'm sorry.
Please.
If basically what we're saying is like, let's just take three numbers. If you had a 3-number list, 1, 3, 2, then what you would do is you would put 1 at the top, and then 3 on the bottom left, and 2 on the bottom right. But then you would immediately see, oh, well, 3 is greater than the 1, so those two would have to flip.
Okay, so 3
So now you would have
top.
3 on the top, and then 1 on the left, and 2 on the right.
Yeah, you're floating your bigger numbers up to the top.
Yeah, it's not a max heap until it's settled. So when you've got that 1, 2, 3 situation, that's not a max heap. It's not a max heap until that parent is the topmost point.
Okay. Yes.
And then when we pluck that point off, we take that 3 off, we cut the head off, then we have to decide which one's bigger, 2 or 1. And we're going to pluck that 2 up there, and now it's got a child of 1. So that's a simple example, but you can imagine if you've got a much bigger heap, like say you've got 100 million nodes in your tree, you always know that the root of the tree is the biggest number. And the rest of it is mostly sorted. So it's not great. It could have some problems. It may not be that even depending on your use case or your input data. But once you pluck that top node off, now you know that either the left node or the right node is going to be the next biggest number. So you have to compare those two. And whatever one wins, you're going to make that the new root node. And then the rest of your heap is still mostly sorted. So it's taking advantage of this case where we know that things that are mostly in sorted order, we could take a couple shortcuts on.
Okay, so that's the key point. Is it's not that these things have to be in order going down the tree. Not like if we said the 1, 2, 3 thing, right? It's not like you have to have 3 and then 1 on the left and 2 on the right. The order of that next level doesn't matter. It's just that it's smaller than that top one.
Yeah, it's that every parent is always bigger than any of its children, bigger or equal to its children.
And it's only got 2 children because we're looking at like a binary tree, essentially.
Yep, binary tree, but it's not a binary search tree. So it doesn't mean the left is bigger than the right, because we don't want to go to that level of sorting the tree, because then we have another sorting algorithm on our hands. It's just we do a cheap first pass at building this heap up, which is faster than a sort, but isn't very accurate. And then we go through and we only have to look at one depth level of that tree whenever we pluck the root off.
Yep, makes sense.
So it's just kind of a cool conceptual algorithm, which I thought was really cool when I kind of figured out what was going on there. I started programming this at Panera, but then I saw how late it got. This merge sort took me forever.
You're like, dude, you got to get off our Wi-Fi.
Yeah. So, as for strengths, it's got a better worst case scenario for Quicksort. So Quicksort, you remember that had the n squared worst case scenario where we have to look at every node. In this case, it's always O log n. And it can also be done in place. So it's great for memory. So it's O of 1 again. And it performs worst case scenario better than Quicksort. And so you would use this in a case where you want consistency. So Quicksort is going to be faster for a lot of average kind of normal everyday use cases. It's going to be faster than Heapsort and even faster than merge sort in a lot of cases. However, if you really want to protect yourself from that worst case scenario, then this would be a good substitute for Quicksort, because you're not going to get dinged. Maybe slower on average, but you're never going to get that worst case scenario where it takes billions of seconds to come back.
So I have a question though, and I don't know if in any of your research you found this though, but if merge sort was like the default go-to, but this one has the same best, average, and worst time complexity, but better space complexity, why wouldn't Heapsort be our default go-to?
That's a good question.
Maybe?
Well, I think it might even go back to what he led this off with, where he's like, here's a side note, the stable part. This is not stable, so you're not guaranteed secondary sorts on this kind of stuff.
Yeah, for sure.
Whereas I believe with the merge sort, you do have that.
Yeah, and sometimes there are like variants of these things. Like each one of these guys, you can almost find like a stable version of, and even though a lot of the ones that are normally recursive, you can find like a non-recursive or an iterative version. But a lot of times they are super complicated and just weird.
Well, and they probably also sacrifice pieces for others, right? Like either storage or something. You're always going to give up something to gain something else, right?
Yeah, and I should mention too on those big O times, like the average big O, which is funny because big O is worst case. Anyway, big O, the average case for Quicksort and for Heapsort are the same. However, in practice, Quicksort is almost always faster than Heapsort. So even though they have the same exact numbers, like when it comes down to like sorting real numbers, so like with real data sets, like you should see in practice that Quicksort performing better, and it's still got the same space considerations there.
Well, that's also because when you're talking about big O notation, and this goes back in my brain will probably, and I'll probably say this wrong, but you throw out insignificant things. So basically things that aren't multiplied values, you kind of just toss away, right? So anything that might have been 6 operations on one, but 4 on the other, that you just get rid of those, right? Like you're not going to do an n+4 if it's not some sort of factor of the n part of the big O notation. It just gets chopped off. So even if there were 50 extra steps in doing something, it's insignificant in terms of big O notation. So if I remember correctly.
And I was just looking too. I was seeing that merge sort is really nice for sequential type data storage. So if you've got an array with those numbers right next to each other, then it's really efficient for kind of hopping back and forth. Whereas if you've got like say a spinning disk and you're doing something like on a heap sort, just because of the nature of it, you're looking at basically like something like a linked list. So that stuff could end up in very different spots in memory. And so that's part of the consideration there. So I don't have a firm like authoritative answer on this, but my guess is that that merge sort is going to just perform faster on average than heap sort, like in real world use cases.
Okay. So when would you use this thing?
I lost my notes.
That's it.
It's basically when you want quick sort, but you want to protect yourself from that worst case scenario. So if you, if you want that in place, that's the big selling point, I think, for an over merge sort is like if you want to be able to do stuff without adding that additional layer of overhead and memory, then I think this would be a good choice.
Okay, cool. All right. And with that, it's time for us to give our little bag. For all those that have written in and given us a review, there were some excellent ones. You know, we get messages saying that, you know, we've helped people change their lives and their careers and all that kind of stuff. And it seriously is awesome to read that kind of stuff, right? Like we love being able to help people advance their careers or make the switch or whatever. So, you know, if you find that we're helping you out in some way and you want to give back, please do go leave us a review. You can do that at codingblocks.net/review. And we read them all and we appreciate it. We take the feedback to heart and, you know, thank you.
Okay. And so with that, it's time to head into my favorite portion of the show. Survey says. All right. So last episode, we asked, now that you've had some time to digest the news, how do you feel about Microsoft's acquisition of GitHub? And your choices were: very excited, looking forward to the awesome things Microsoft will add to GitHub, or I'm concerned, but not enough to do anything about it yet, or I don't care at all. Should I? Or, oh my God, the sky is falling. Why? How could we let this happen? Or, I've already packed up my code and moved to GitLab. So, Alan, I think Joe went first. So you're up first this time.
Man, I honestly have no idea on this one. I'm going to say I don't care at all. Should I? And I'm going to go with, just because I really don't think people care that much, I'm going to say 40%.
Okay.
Joe?
All right, I'm going to say I'm concerned, but not enough to do anything about it yet. Dun, dun, dun. And I'm going to put it at a strong 32%.
That's not that strong. You got to man up.
All right. And survey says you're both wrong.
Really?
Oh, wow.
So I don't care was the top answer.
Doggone it.
But you were over optimistic in your percentage.
Showcase showdown. I lost.
Yeah. So Price is Right rules, you lost. It was that's the beauty of combining two game shows. Right? It really makes it confusing. Combine the Price is Right with Family Feud. And you're like, what?
Yeah.
That's our specialty.
Something's off.
Yeah. So, yeah, by Price is Right rules, you went over. It was 36%.
Oh, so close.
Yeah,
Wow.
I was really hoping that he was going to, Joe was going to $1 it, that'd be hilarious.
So what was number 2 there?
With this part, I liked. People were optimistic about it.
Very excited, huh?
All right.
Excited was the second highest.
30%?
30%.
Very nice. So we've got 66% of the votes on those two.
Yep.
So that's both in either I don't care or this is awesome.
Yeah, and then the other part, Joe had the third highest.
What was that at 20s?
Yeah, it was like 27%. So
Okay.
most of the votes were like right in there. Which I guess the good news to that is a lot of people haven't like packed up and moved to GitLab or to a Bitbucket or there were some comments. Well, I guess there were some comments though on the show notes for that one about like, hey, we didn't include like every other code hosting facility out there. Namely Bitbucket came up.
Right.
Mm-hmm.
I will say this. Anybody who's worked in VSTS has got to be somewhat impressed with how good a job Microsoft has done with source control type stuff and how it integrates things. So if they kind of keep status quo with that on GitHub, like I think there is good reason to be excited about it.
Yep. And I've talked to a few people that were kind of close with some of the stuff that's going on over there, and they said that things aren't going to be changing radically anytime soon.
Cool.
So
Awesome.
a little wink, wink, nudge, nudge there. But I've got an account on every platform. Just go out on the game if nothing else, right?
All right. So with that, we'll get to this episode survey, which is what is your most productive season? So your choices are, I don't know if you're going to be able to guess these, but I'm going to tell you what they are anyways. Spring, because it's the best way to avoid the pollen. Or summer, let me stay behind my keyboard in the nice air-conditioned room. Or fall, the sky or leaves are falling. Safer to stay inside. Or winter, because Olaf scares me. I'm not going out there. Or seasons, we don't have any seasons here.
I'm going to be upset if that's the winning answer because I'm going to move.
Well, I mean, you're thinking that not having seasons could be a good thing, though. I mean, if you could live in a colder region of the world and not have any seasons,
that's a good point.
I really wish that you did.
I wasn't thinking Greenland when that answer came up. Which, by the way, why is that called Greenland? All right. Anyways, yes. All right, so diving back in here, we are now going to do the binary search. So we're out of the sorting algorithms. Now we're going into these searching ones. And on this one, this is like the one that I actually remember from school. There's very little that sticks in my mind from school, but this one was fairly easy for me to digest back in the day. So here's the thing with about a binary search is you have a list, and that list has to be sorted first. Now, this isn't terrible if your list is already sorted in binary tree format because it will be sorted for you. And this is another one of those divide and conquer algorithms. So really all you're doing in this thing is splitting the list in half and keep splitting the list in half and looking for the number or whatever you were searching for, whatever that search term was. So let's take a pretty simple example here. So you've got 1, 3, 5, 7, 9, 11. So where I put that pause in there is where you'd split this. So let's say that you're searching for the number 9. So you're going to take this 1, 3, 5, split 7, 9, 11. Is the 9 bigger than the numbers in that left list? Yes. Okay, then you can toss that left list out. It's not going to be there. All right. Now you're going to split what's left in the right list, and you're going to say 7, 9, 11, split it down the middle. Well, you can't do that because you can't cut 9 in half, right? So probably what you're going to do is take the first 2 of that. So you're going to have 7 and 9 on the left, and you'll have 11 on the right. So the number that you're looking for, 9, was it greater than or was it less than 11? Yeah, okay, throw away the 11 list, right? So now you have 7 and 9. You're going to split that one down the middle so that you have 7 on the left, 9 on the right. You compare those. Okay, 9's obviously the one on the right, and that's how you find it. So it's a divide and conquer. You literally just keep splitting it in half until you get to where it is. So it's pretty easy. I mean, I don't think I put down any of the complexity on this, but I have to imagine this is probably.
There's divide 2. There's your hint.
Yeah, that's what I was going to say. I mean, that would be what, log n?
Yep.
So.
And I really like this one. The example I always heard in school was like the phone book example. Like I don't know if you guys have phone books anymore. I haven't seen one of those in the last 10 years. But the idea is like if I'm trying to look up, say Carrie Underwood, right, in the phone book here, or what I would do is if I was smart about it, I would flip open to the middle and I'd say, oh nope, now I'm in the Outlaws. Let me flip to the right. So you flip a big chunk of the book over and like, okay, well, now I'm in the Zach, so I went too far. So you would flip back, and so eventually you're going to end up at the Underwoods in the minimum number of steps. However, like things get crazy. So if you actually know, for example, like the phone book is kind of a bad example because you know that certain letters are more prominent than others. So you could actually do a little bit better job by not splitting right for the middle. So you could actually do better than log n there. But for the most case, like that's just a really good way of going. And it's amazing to me how much binary search comes up in other algorithms. Because if you need to find some sort of value to do something, then a good way of doing that is to basically keep a list sorted or build up a sorted list as you go along so you can find things easily. And so I think that's a big part of why this particular algorithm was listed with all these other algorithms that we're talking about. It just comes up all the time.
Yeah, it's simple and efficient, which is not something that you necessarily hear a lot, right? Like usually simplicity does not equal efficiency.
And I can give you a real world use case where binary search comes in because we talked about it last episode.
With phone books, not real world?
With
Get
search.
bisect.
Get bisect. There you go.
Get bisect uses a binary search
Awesome.
effectively. I mean, it's kind of like, but going along your divide and conquer. You're doing the searching, but it's doing the dividing.
Mm-hmm.
Awesome. So that was it. Like that was probably the easiest thing that I'd seen in all these.
So next we're going to get into graph traversal. So we've talked about some sorting algorithms. We've talked about some searching algorithms. So what about something more complicated like graphs? So like a lot of things in computer science, we'll put a lot of fancy words on something that's rather simple. So graph traversal is just the concept of navigating the graph. So this gets tricky. We can either traverse a graph via recursion or via an iterator. And remember what I said before about recursion, right? Our little alarm bells are going off because we risk a stack overflow, so we need to choose wisely. So what is this? Let's think about your family tree. It shouldn't be a stick. So your family tree. There are a couple ways that you could search that tree. Or graph. Your family graph. Everybody calls it a family tree, but one way.
Here in the deep South.
Yeah.
Right.
That's your family stick.
Oh, God.
So one way might be to go as far down one path as possible before you go to the next node. So consider this, you're thinking of you're into researching your ancestry. So you explore the lineage as far back as you can go on your mother's side of the family before you start exploring your father's side. Okay. That is a depth first search. Another type of search that we might do might be to search first on all of the nodes on the same level before going to the next. So again, let's consider your family as an example, but this time you might be more inclined to ask closer family members for money or help before you go further down the tree. So in other words, you might be more likely to ask a sibling for help before you would go to your parents. And you might be more willing to ask your parents before you go to your grandparents, etc. Right? That is a breadth first search. So that is my introduction to depth first and breadth first search. So how about we take a deeper dive into depth first?
Yeah, so looking at depth first search, so like Outlaw said, is where you basically go down the length of the tree. And pretty much when I think about a tree, I actually think about it inverted, so it looks more like the roots of the tree. I don't know about you guys. Even with the family tree example, like I always think of it kind of going down. So it's kind of funny.
Yep, the single node is at the top, and then everything falls up underneath it.
Yeah. And when we talk about depth first searches, that works for binary trees as well as trees that have different amount of branches, and it works for things that aren't even trees, like graphs. Whether or not they have cycles is up to you. What can you say about it? To me, like I almost always think depth first. So whenever I'm doing a problem, in like say code wars or something, like this is my go-to. And I think that depth first just kind of fits better with my mental model because it's easier for me to do depth first without having any sort of storage associated with it. And that works well for trees and doesn't work at all for graphs. And the deal there is that if you've got a tree and you know that there are no cycles in that, so it's a true tree, then you don't actually have to keep track of your path because you can know that you could always get back to the root by just going to your parent. So you don't need to know your position. Now, in some cases, like if you're trying to track your path or you want to store a path or you want to know what nodes you hit along the way and you're not just searching for a single value, then that's a different situation. You're going to need to keep some sort of array or stack there to keep that travel history. So it's kind of a nice thing if you're doing code wars or an interview. If you just need the value, depth first works great because you don't need to know anything about where you are. It's recursive, so there's a possibility for either an infinite loop there or blowing your stack. However, if you're in a language that supports tail recursion, then you can pass primitive values and get around that all entirely. And then you just have to worry about running forever. Actually, by the way, it's kind of funny. I don't know if you guys looked up like BFS versus DFS, but some of the examples they give is like, well, depth first, if you've got an infinite amount of data and your data you're looking for is right here at the top level, but it's to the right, you're never going to get there because you're just going to go down, down, and down forever. Like, well, I mean, that applies for breadth first too, right? If you've got an infinite number of children. So
yeah,
that's what I bring it up.
Yeah, I agree. That's unless you know your data super well and where the stuff is going to live in it.
No. I'm going to give you a hypothetical situation that can never exist to prove why your solution sucks.
Man, I can't stand that stuff.
Yeah, I didn't really understand why. And maybe I'm like misunderstanding something fundamental, but it was just kind of funny to see that even come up at all because I kind of felt like, well, what if you got infinite data and you want to find the biggest number? You're never going to find it because you don't know. It's like, well,
if you have infinite data, you'll never find it because it's infinite.
It's turtles all the way down.
That's right.
I could talk about stuff that's never going to happen all the time. Insert joke about love life here or something.
Wow.
Oh man.
So we talked about stack. Another way to kind of get around having that to keep that actual path is in memory is to have a pointer back up to the parent, but then that means more maintenance, which is annoying. And if you've got a cyclic graph, then that's doubly annoying because now you've got potentially more than one parent. The idea of a parent doesn't even make sense anymore. And then I want to mention too, there's lots of different kind of trees, and so there's red black trees and binary search trees, and depth first search works for all of those guys, but it gets really hard to kind of talk about these things without going into those sort of details. So we'll keep it kind of high here.
Hey, wait. So you mentioned the recursion with the stack, and then you also mentioned the pointers back to the parents. Is there any reason you choose one over the other?
Yeah, I mean, if you have a tree, then pointers are okay, but whenever you have to insert, you have to maintain that stuff. So if that's a tree you're bumping around all the time, it's annoying. It's just like a double linked list. It's just you have to keep up with that stuff. It's extra work to do. It's extra overhead that for the most part is unnecessary depending on the kind of tasks that you're doing. The stack thing is nice.
Go ahead.
Stack is nice if you need to keep your path. So if you need to find like the path to a certain node, that's a great way to go. But if you don't need to know the path and you don't need to know how you got there, then you don't need to store either one of those, and you can just keep going down forever, and you know you could always get to any node from any other node without having to keep track of your path at all. So I like this idea of like you kind of traveling amongst these nodes and never actually knowing where you are in the tree, because it doesn't really matter.
But I guess the thing I wanted to point out is the pointer. Yeah, it's annoying, but you're never going to run into a Stack Overflow issue with that, right? Whereas with your recursion, if your tree is infinite levels deep, then it's there's going to be some point where you're going to hit a Stack Overflow if you're doing the recursive method. It is the only thing I was getting at there. With the pointer, you don't run into that particular problem.
Yep, and I should mention too, one thing that's nice about having a stack is actually it lets you easily know what depth you're at. So a lot of times when people talk about like searching trees, like they'll even say like max depth 11, and you'll just say, after a certain depth, you'll see this a lot of times in like game theory, or like talking about like chess simulations or stuff like that, and say like, don't go all the way down to all the possibilities of moves. Only look like 4 or 5 or 10 or whatever, some sort of number levels into the tree, because like it's really common for infinite trees to come up, which is also funny to me. Not necessarily infinite, but just trees so large that it's not worth dealing with. And so you might set a max level there. If you've got a stack, then you can get to that point. The alternative there is to try to maintain that depth whenever you kind of move nodes around and stuff, which is annoying because you have to maintain that. And when I say annoying, I mean computationally annoying, like your processor is grunting about it. So it's simple, and I like it because, as far as I know, I don't think there's a way to do a breadth first search without keeping track of where you've been. I could be wrong about that. Guess we'll find out here in a minute. But it's I want to point out too that it's worse at finding closer data points. So in like the example that Ella gave of the family tree, like if you go down your sister's side of the family first, and you're going to be like checking all these people for money, but really you would have been better off going to your brother and searching for something that's closer to your root node. So it's just not good at finding things like that where you suspect that your data might be closer to the root node. It's better at finding things that are deeper. And what else?
I have an idea as to like what you think you're going to be, where your result might be.
Yep.
By the way, these types of questions are very, what I mentioned earlier, like interview type questions with big tech companies. This is the kind of stuff that you'll get hit with, right? Like, I want to find all the nodes with this value. How would you do it? You're given a binary tree. How would you go do this? And how would you know that you've been there? And how would you there's a lot of things that you run into with this. And so if you haven't visited this stuff a lot, like I highly recommend this book because he does a great job of simplifying some of these sort of hard to visualize and conceptualize things that we're talking about that you're probably going to you're scratching your head on your way to work right now. Like, oh my God, they just said a lot of numbers and they rearrange those numbers a lot of times. But
13524.
Right. No, wait, it should have been 3245.
Yep.
So no, he does.
Combination of my luggage.
I love that.
I want to mention too, we didn't really go into it, but a big deal with trees is kind of keeping them balanced, and even graphs too. Like you can imagine, like if a tree all it ever has is like left children, then that's not a tree. That's that stick we were talking about, right? So pretty much everything's going to be bad in that kind of stick case. So balancing trees is a big deal, and a lot of algorithms, like for even creating trees, are going to deal with that. But we're not talking about those tonight.
You went dark on us. There you go. You came back. All right, so. Then mine, he did the depth first, and I'm going to talk about the breadth first, which Michael hit on just briefly a little while ago. And this is interesting. What Joe said is you have to track where you're at as you're going down. You have to know at each level, because what the breadth first search is, instead of like what Michael said, where you want to search all your grandmother's grandchildren all the way down before you go to your grandpa's children or whatever. Instead of this, you're going to search at every single level before you go down the next level. You're going to search all the nodes on a level before you go down the next level. So if you're on the top, right, like your great-great-grandpa, right, he's the very top of this thing. You're going to look at his, it's not there. Okay, now you're going to go to the next one, which is going to be his children, right? So you're going to look through every one of those children at that level, that second level, before you go down to the next level. So that's why it's breadth first. You're going all the way across the nodes on a particular level before you step down to the next level. So It's just literally flipping which direction you're going, right? So instead of going down, you're just going sideways on every level.
And
Now,
I think the difference there is kind of like once you end up hitting, like, let's say your aunts and uncles, so like a generation above you, you kind of go aunt, uncle, aunt, uncle, aunt, uncle. Now it's time to start hitting their kids with your nieces and nephews, or no, sorry, your cousins. Then you need to know, like, okay, I've hit this aunt or this uncle already. And I don't think that there's any real good way of knowing. I could be wrong. I mean, maybe you can just track up. Maybe there's something simple I'm missing there, but I think it's kind of a pain in the butt to know what is next for you.
actually, I don't think it's terrible. Like if you look at the example that he had, it's basically just a queue. Like it's not that hard. Basically, you add the the node onto the queue, and then you look at the left first, and then you look at the right. After you're done with that, then or you do after you're done with that, then you're going to pop the left one onto the node, and you're going to look at its left and right, and the same with the right. So it's not as complicated as it seems. I think that Wikipedia even had an example on this, or they showed some pseudocode on it. So I've got a link to that as well. But it's not bad. It seems like it would be, but if you just use a simple queue to where you're just popping or pushing things onto the queue and then popping things off, it's not bad going across those.
Well, what I think I'm kind of getting at is like you say, okay, let's start with my grandparents, right? And we check with them. Okay, we'll move on. So now we go down to your aunts and uncles. So now in your queue, what you're going to do is you're going to say, aunt, we'll check with them. Uncle, check with them. Aunt, check with them. Uncle, check with them. But we don't pop them off the queue, even though we've dealt with them, because now we need to go back and do their children, right? So it's kind of like we need to go, there's this notion of going back and then popping off the queue, because you want to deal with each as it comes along and then go back to deal with their children in that particular order.
I got you. Well,
I was
So
thinking
it's kind of like you add to the queue.
tree into the queue. So you're taking this tree and you're basically like making it into a stick. So you are popping them off.
But you have to deal with them as you add them to the queue. So you say like, hey, Uncle Tom, can I borrow $20? No? Okay, I'm going to add you to this queue because I'm going to come get your kids later. Right? You say, all right, Aunt Marjorie, can I borrow $20? No? Okay, well, you're next. After I talk to Tom's kids, I'm coming back to your kids.
So looking at the code, let's see. So the breadth first search, so they have this thing, they add the root to the queue while the queue dot count is greater than 0. Move the next item from the queue. It checks to see if the left node has a value. If it does, then it adds it. If the right node has a value, then it adds that.
Mm-hmm.
And if we load it up just like that, we'll have a completely different.
Yeah, it's basically making a stick out of the tree before it bothers to do any searching.
Right.
But how do you get to that second generation? So you queue up aunt, uncle. That's all the children of your grandparents. At what point, do you go on to their children? Because if you just pop them off, as you say, like, hey, Uncle Tom, $20. No, Aunt Marjorie, $20. As you drop those guys off the list, at what point do you go deal with their kids? Because you've kind of lost track of them.
I think so. Looking at the way this thing happens is it pops the top one off as it gets to it. So for instance, if you're at the root, so the grandparent or whatever, it's at the root, it adds it to the queue. Okay, now it's going to start operating on that thing and immediately pops it off the queue, and that is now the current node that you're on. And then it's going to say, okay, now I need his children, and I'm going to pop those or push those onto the queue now. So your left and your right get added, right? Then you're going to work on those two items in the queue at that point. So if at the top you were 0, you added it to the queue, you immediately took it off the queue, and now you say, give me the left and right. So that's going to be 1 and 2 that you just pushed onto the queue, right? As you operate on, let's say that 2 was the last one that was added. So you're going to
when I pop them off, that's when I add their children.
Correct. So you're going to pop that. It's actually going to happen after you pop both of them off, I believe, because then you're going to take those nodes and you're going to add it back to the queue, right?
Okay, that's where I was kind of saying where it's like, okay, we would deal with one and I'll be back for you later to deal with your kids. And the way you do that is you say like, hey, Uncle Tom, $20? No? Okay, I'm adding your kids to the queue now, but I'll be back after I talk to Aunt Marjorie.
Right.
I'm going to shake you down.
I think that's exactly how that works.
So why I like depth first, or I like depth first search better is because I can just say like, Uncle Tom, $20, no problem. I'm going to your kids. Hey, you got $20? No, okay, I'm going back to your parent. So I don't need to kind of keep track. There's no queue involved in some situations unless I'm doing something specific like needing to keep track. I could just say like, hey, Uncle Tom, go to your kids, which Uncle Tom knows about, and that kid potentially knows about his parent, or just the recursive nature of the algorithm knows to go back up. And so I don't have to keep track of any special data structure there. But you need data structure for breadth first.
There is a flip side to this, right? And this is where just knowing and understanding your data comes into play. So in a real world example, you would probably start keeping track of, hey, where did I find these things, right? If I'm a company that has to crunch tons and tons of information and there's all these searches always going on, then you're probably going to want to start trying to keep stats of, hey, where in these trees was this data found, right? Because it might be, while the depth first is easier to do and kind of less complicated to do in a sense, it might also be the least efficient, because it might be that everything's always on the second level, right? Like most of the time you find everything on the second level, but you just traversed 50 levels, going down trying to find data, when all you really need to do is go across 4 different nodes, right? So it's one of those things to where there's not one that's better than the other. It literally just depends on where the results are in the data, and the only way you'll ever know that is analyzing. And it might be that it's completely random and you have no option, right?
So let's put some context to this. If you were saying like, hey, if you're trying to think of like an example, like, well, why would the data probably be like only one level deep, right? So let's say I connect with Alan on Facebook, for example, right? Well, they might want to show me recommendations of other people that I might likely be friends with. Now, there's a higher probability that the people that I might be friends with are going to be 1 degree away from Alan, more likely than if you went through an entire lineage of Alan's friendship and went like 50 levels deep and like, oh yeah, here's this person that they both know. That might happen, but chances are higher that it's going to be, 1 degree away.
Yeah. So exactly what you're saying. If you look at my direct friends and you look at Joe Zach's direct friends, chances of you finding somebody that you know in common is going to be in that first level, right? As opposed to, oh, well, I'm friends with somebody that's friends with somebody else that's friends with somebody else. That's not going to be as useful. And so that's an excellent example. And LinkedIn does the same type thing, right? So
any kind of social media.
Yeah. So that's excellent. And again, on that one, it's kind of easy to see that one's going to be there. But if you, like I said, if you have other data complexity problems at a company or something, you're not going to know which is better until you kind of store your findings of doing the searches, right? Which is something that companies that deal with a lot of data probably do. And then other companies don't pay attention to it, and they might be just using a ton of processing power improperly. So.
And if you're looking at harder algorithms, like good luck doing them without some sort of sorting or some sort of graph searching or tree searching going on.
Yep. So,
and we talked about both of these in relation to like binary trees, but I mean, you can envision how it could work to where like each node might have more than just 2 siblings or, ancestors. Blah, 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 blah.
Yes.
I can't say that word, but you know the word I'm trying to say.
Yes.
So you say it in your head and then it sounds all right.
That's very true.
But yeah, like instead of it having 2 parents, if it was, a larger family.
Yes. So in short, DFS rules, BFS rules, because it's hard for the programmer.
It's not that much harder.
It's that extra 15 minutes in that algorithm that make all the difference.
Oh, man. So I can't remember what I found on this one as far as I put on there that I think it's either, why in the world would I have put O sub 1 or O sub n squared? Those are kind of At opposite ends of the spectrum.
Well, that's okay. I said for selection sort, you didn't have to search the last one. So, I mean, we both said move on.
I'm just going to go ahead and delete this line because I don't know what I was doing there.
It depends. It depends a lot on your graph. Like if you've got a sorted graph, then your time to search something could be really fast because like left is smaller and right is bigger, and so you're looking at that's like one of those halving problems. You're constantly halving your problems. So you're looking at O of n. But if you've got no sorted data and you don't care where you put stuff into the graph, then it's O of 1 because just throw it over there.
I appreciate you making me feel better about that.
I'm on board. It's this Diet Mountain Dew. I've been trying this with podcasting.
Your complexity is like really complex when you get out of O of N and you get into other letters.
So the V and the E's and all that garbage.
Yeah. Worst case performance they have is O of absolute V equals O of B to the D.
Yeah, man. The V were the vertices, and I don't know what the
hilarious.
B's and the D's were. And I think that's where I was like, well, it's O sub something.
Yeah.
O sub something.
A lot of tree algorithms are like that. Will be like M times N, where M is the depth of the tree.
Yeah.
I think where you probably got that sentence is there was a space-time complexity analysis sentence here in the Wikipedia article where they said the time complexity can be expressed as O of absolute V plus O of absolute E, since every vertex and edge will be explored in the worst case scenario. So absolute V is the number of vertices and absolute E is the number of edges. So note that O of absolute E may vary between O of 1 and O of absolute V squared.
Oh, so I did put it in there kind of like that.
Depending on how sparse the input graph is.
It makes no sense.
And I wonder if I'm reading that right. Like, is it supposed to be absolute V and absolute E or just some
E
weird
V.
symbol of O of E, V plus E?
It's Wikipedia.
I don't
Because
remember.
why would the number of vertices be negative or the number of edges be negative?
Yeah, it can't be absolute, right?
Why would it be absolute?
Yeah,
you can have negative weights you could have negative distances on a graph, like wormholes and stuff.
Well, okay, now we're getting ahead of ourselves and we're talking about like things like Dijkstra's or the Bellman-Ford where you have weights when you traverse the graph, right? But we're not talking about that here.
You can have negative distances though. Like it doesn't make sense on like a map, like a Google map.
I don't know if you just
As the wormholes and quarks change everything. Once the Q continuum comes into play and
Joe, we are not talking about that
today on Star Wars.
Sorry, that's my other podcast.
Oh yeah, I'm sorry.
Oh, that's awesome. Yeah. So with that, we've covered all the. Man, I thought this was going to go faster than it did. We've covered what we think what
Rob Connery.
Rob Connery thinks are probably some good algorithms and sorting things to know about and search algorithms that are sort of the building blocks for understanding more complex things, which we may cover here in a future episode. We got tons of links in the resources we like section.
As always, there will be a lot of links in our episode show notes. So, yeah, give those a look.
Yep.
Don't forget that discount code too for the digital version of the Imposter's Handbook. It's Happy Imposters, however you spell that.
Happy Imposters. Was there a space in there?
No space, but you have to ask Google about how to spell imposter.
It's with an E. It always throws Joe, but it's with an E.
Happy Imposters.
Give you a hint.
No space, and that gives you the discount for the book, which is most excellent. And they've actually got a new version coming out sometime in the near future. So
maybe Joe, if you pronounced it as imposter, could remember how to spell it.
Posters, yes.
Yeah, the Imposter's Handbook.
I will give that a shot. No promises.
All right. And with that, it's on to my favorite part of the show. It's the tip of the week. And so mine being that we talked about search engines and all that stuff last episode, touch back on it this episode. One of the most important parts of getting things into a search engine or of sorts, if you're going to do such a thing, is ETLing, extracting, transforming, and loading that data into your search engine. And if you go the Elasticsearch route, they actually have a tool built for this. It's called Logstash. And if you're not aware of it, it's pretty interesting. I mean, a lot of people go to their database first to try and, use, if you're in SQL Server, something like SSIS to try and do this kind of stuff. Well, Logstash is a pretty simple way to do this, and I highly recommend you check it out. So I'll have a link to that here in the show notes.
All right. And for my tip of the week, this is a Visual Studio Code tip, or if you prefer me just to call it VS Code or maybe just code, we can do that too. This is a way to, if you want to write Markdown in code, Visual Studio Code, you can preview it by pressing Control-Shift-P on a PC or Command-Shift-P on a Mac. And you can preview your Markdown, which is really great. So if you're writing like a README for your next great project, you can preview that Markdown.
Doesn't that screw with the command palette command? I think Control-Shift-P is how you pull up the command palette.
Let's find out.
Yeah, let's all open up code, see it's faster. Joe's
Boom.
It's
Control-Shift-P is, yeah.
Yeah, that brings up the command palette.
Oh, you know what? Okay. When you do that, though, it'll bring up a drop-down where you can type in preview Markdown.
Okay, that's
what I forgot.
Okay, so just a heads up, then I'm going to add to that tip. I love that. So Command-Shift-P or
I forgot to
Control-Shift-P.
say that. I actually had that written down.
Okay, cool. So that's actually the shortcut to open up the command palette. And so you can do all kinds of stuff in there. Like what you were saying, you type in preview or Markdown or whatever, right? I assume.
Yeah, just type in like Markdown and then you'll get preview Markdown.
Yep. So what I use that for a lot of times, and I'm just going to piggyback on this because I love it, is if I have a JSON document, man, formatting JSON always feels like there's never a tool around to do it. What you can do is if you take JSON that you get from maybe you were looking in Chrome developer tools and you get a payload back, you can take that, paste it in, do Control-Shift-P, and then change, I think it's document. If you type in document, it'll say change document type or something. Then you just choose JSON and then format it directly. So I don't like using my mouse. And so Command-Shift-P or Control-Shift-P is a way to get to that command palette to do those things quickly.
Yeah, I didn't know that VS Code plugins were available for tips, man. I got tips for days now. Watch out, world.
I've talked about them before. How could you not know that?
Yeah, man.
Yeah, but now I'm this Mountain Dew, man. Like I'm awake and out of. I've never been this awake at this point in the show before. So it's sorting and stuff.
So you're tossing your last tip here, and we're going with some VS Code stuff.
No, this is a great tip. This is Bookmark Navigator, and this was sent to me by Neil Spackman, who said, "Hey, check out my plugin," and I freaking love it. And what I do on my Mac, or I guess Windows too, is I hit Control B, and it pops down like a little search, kind of like that command palette, where I can start typing in my bookmarks. So like if I've got some documentation or something in there, like I've got a bunch of bookmarks and they're not exactly sorted very well, but now I can kind of treat it like Spotlight on Mac or kind of Cortana, where I hit like Control B and I start typing doc or VSTS or whatever and just hit enter just like by typing the minimum amount of letters. So it lets me kind of just do like a really quick search through my bookmarks. So now I've started like getting better about actually adding bookmarks to common sites rather than like using Google for the same thing by hitting like Control T and then typing and then like, oh God, I didn't know that was in my history. And, so it's just really nice. It works out really well. And so we'll have a link to that in the show notes. And thank you, Neil.
Very cool. That looks very useful.
Yeah, true that.
Awesome.
All right. So we've been talking about some algorithms that you should probably already know. And if not, hope now we've helped you to know them. These are algorithms that you're probably going to come across at least in an interview, if nowhere else. But I hope you enjoyed it. And with that, subscribe to us on iTunes, Stitcher, and more using your favorite podcast app. Be sure to leave us a review by visiting www.codingblocks.net/review.
Yep. And while you're up there, go ahead and check out our extremely detailed show notes, our examples, discussions, and more.
And send your feedback, questions, and rants to the Slack channel, codingblocks.slack.com. And you can actually sign up for the Slack by going to codingblocks.net/Slack. So hopefully that didn't confuse you. Make sure to follow us on Twitter at codingblocks, or head over to codingblocks.net where you can find links to all sorts of stuff like the Slack. So you don't even have to remember anything except for codingblocks.net.